Good morning, friends. Today we are going to learn a new, very interesting theory that is molecular orbital theory. So far, we have learned hard theories, VSEPR and VBT theory. So today we are going to learn a very easy theory that is molecular orbital theory. So let us learn that today. Okay, concentrate on the topic. So who actually postulates this molecular orbital theory? Yes, F. Hunt and R. Mulligan proposed the molecular orbital theory. So what is inside that? So far we were discussing about concerning about atoms, right? So in molecular orbital theory, we are concerning about molecule. Okay, so in atomic orbitals, electrons are filling under in atoms, electrons are filling inside the atomic orbital, right? So in the molecule, electrons are filling inside the molecular orbital. That is the first postulate. Okay, so very easy postulate. In the molecule, the electrons are filling inside the molecular orbital. That is the first postulate. Okay, so what is the second postulate? In the second postulate, what they are saying is, as we know that when atomic orbital combine, then we are getting molecular orbital. So atomic orbital of comparable energies and similar symmetry, they will combine, okay, and we will get molecular orbitals, okay. And if you are considering an atom, it is monocentric, means this electron is only influenced by this nucleus, okay, only one nucleus in an atom. But when we are considering the molecule carbon dioxide, HF and all, it has more than one nucleus, so it is polycentric. Molecular orbital, we can say it is polycentric. Atomic orbitals are monocentric. Okay, so now what is the next postulate? It's very easy. So far, we learned in many cases the same thing. How many atomic orbitals are coming, that many molecular orbitals you are going to get. Suppose two atomic orbitals are coming. So you will get two molecular orbitals. That's all. Okay. But these two molecular orbital we can divide into two. One is called bonding molecular orbital and the other one is called antibonding molecular orbital. So let us see antibonding molecular orbitals and bonding molecular orbitals. Look, this case, one example. So 1s orbital, two 1s orbitals are combining. So they have almost equal energy and same symmetry, right? So they are combining. So you are getting two molecular orbitals. So one is called a bonding and the other one is called antibonding molecular orbital. So bonding molecular orbital is having lower energy and highly stable it is compared to antibonding molecular orbitals. It is having higher energy. Why? In bonding molecular orbitals, look here, in bonding molecular orbitals, the electrons are concentrated. The electrons are concentrated in between the nucleus, so the attraction will be maximum and repulsion will be minimum. Okay, so that the energy is very less for bonding molecular orbital because the electrons are influenced by these two nucleus. So minimum repulsion, maximum attraction. So the bonding molecular orbital is having less energy. And look here, what is happening in between the nucleus? Nothing is there, right? The place where the probability of finding electron is zero, this is called a node. So you can see a node between this, right? So the electrons will be here, not in between the nucleus, that is far away here and there in the, yes, here and there, right? So what will happen? The attraction should not be maximum, the repulsion will be maximum. So when the repulsion is maximum, it will get higher energy and the stability will be less. Okay, that is the case of an antibonding molecular orbital. So bonding molecular orbital is having less energy because electron is concentrated in between the nucleus to get maximum attraction. Let us see another figure also. Look at this figure. So what is happening? This is energy, lower energy and higher energy. So when this represent the atomic orbitals. So atomic orbitals are comparing and one is going down, one is going up. Because one is having lower energy even than the atom. Look at the energy of the atom. This represents the energy of that. So it is having lower energy than the atom. Okay, and so the bonding molecular orbitals are stable and the antibonding molecular orbitals are higher, having higher energy. It's going up than the atomic orbitals. Okay, sigma represent the bonding molecular orbital. This is antibonding molecular orbitals. Okay, so now let us look at the other postulates. There is one more postulate, that's molecular atomic orbitals. We know that electrons are filling according to three principles: Hund's rule, Pauli's exclusion principle, and Aufbau principle, right? So what in the molecular orbital we are following the same thing. We are following these three rules and the electrons are filling inside according to these three rules. So let us go for a recap of these all theories. So the Aufbau principle, what was Aufbau principle? In Aufbau principle, the electrons are filling according to the increasing order of energy, okay, from the lowest energy to the highest energy, like that the electrons are filling 1s, 2s, 2p, 3s, in that order. That same order we are following in molecular orbitals while we are filling the electrons. So in Hund's rule, what we have learned is the electrons will first singly occupy, then only pairing up. What was the reason? If you pair up first, there will be repulsion between the electron and the energy will increase. In order to decrease the energy, the electron first singly occupy, then only it will pair up. Okay, so that was Hund's rule. And the next rule was Pauli's exclusion principle. According to him, the electrons must not have same spin. Okay, they must have opposite spin, and all their quantum numbers should not be equal. Okay, for these two electrons, it will be different. At least one quantum number should be different, right? So the if you are doing so, what will happen? The spin quantum number should be different. One is clockwise and one is anti-clockwise. Okay, so this is the correct order. One should be up and one should be down. So these all we are following in molecular orbitals while we are filling the molecular orbitals. Okay. Now let us see one case. Let us take, molecular orbital theory is also called a linear computation of atomic orbitals. Let us see how they are combining. Let us take two examples. That is, one is hydrogen, two atoms we are taking, hydrogen A and hydrogen. This is going to combine now. Okay, so first we have to understand, we are taking a few points from wave mechanics. We cannot learn that in grade level because it is a hard topic. So only one or two lines from wave mechanics we are taking. So atomic orbitals, we are representing here using psi. That is only one thing we are taking. And actually the psi represents the amplitude of electron wave. We know that amplitude, how to determine and all. So that is actually psi, and it is getting from the solution of Schrödinger equation. Okay, we are neglecting that. We'll just understand. First, you only understand this, the atomic orbital we are representing using psi. So you are representing HA, the atomic orbitals of HA atom as psi A and HB atom as psi B. Okay, so you have two atoms, they are going to combine and going to form molecule, and here psi A and psi B are their atomic orbitals. Okay, psi A and psi B. So now this psi A and psi B may combine in two different ways. Okay, either they can add or they can subtract. Okay, either they can add or they'll subtract. Okay, so if they add or subtract, they are forming the molecular orbital only. Okay, psi AB represents the molecular orbital when they combine. So if they are adding psi A plus psi B and forming a molecular orbital, that will represent a bonding molecular orbital that is having less energy. Okay, and if they are, the molecular orbital is formed by subtraction of this atomic orbital, then you will get antibonding molecular orbital. Okay, and then you will get antibonding molecular orbital, and the energy will be high here. That's all. Very simple. This is called a linear combination of atomic orbital. Okay. Now let us see a clear picture of that. Okay. Yes, this is the clear picture of that. What does it say? Look at this. This is psi A, atomic orbit. So the same hydrogen atom we are considering. So if you consider the same hydrogen atom, this is 1s orbital of a psi A, Ha atom, 1s orbital of a Hb hydrogen atom. So it is having one electron, it is also having that one electron is so this part represents the atomic orbitals. Okay, so that one electron here, one down, because we are following the principle we said already. One spin up, Pauli's exclusion principle. Okay, now next Raffco's principle also we are following. According to that, lower energy will fill first. So we will fill the sigma, that is bonding molecular orbital first with. Okay, so if you are considering hydrogen molecule H2, there are total of 2 electrons. So sigma, the 1s orbital, in sigma 1s orbital, you are going to fill, that will be occupied with these 2 electrons, because after the lower energy is filled, then only it is going to fill in the antibonding molecular orbitals. Okay, that's it. Now these are the postulates. Today we are only discussing about the postulates. Now, next day we will clearly, we will understand how to fill the electrons in the molecular orbital and what are the various different type of molecular orbitals and all. Okay, thank you.